Okay, now we are going to go a little bit deeper into the concept of delay models in Verilog, right? And there are different types of delays that are present in general in digital circuits. Now, at some level, you need to understand the concept of gate delays because this will play an important part in timing or timing analysis, as we will see later. Now, what I am going to be talking about over here are some aspects of Verilog that can be used in order to model different kinds of delays. But one very important caveat that I want to give over here is you need to be very careful with how you use these. In practice, it is actually quite rare to use many of the different modeling techniques that are present in Verilog, right? And you would usually be using only extremely simple forms of the models. Why is that? Because as I told you, having complicated delay models in your Verilog code does not actually imply that those complicated models get reflected in hardware. It's usually the other way around. You have certain hardware and you want to be able to model it, which means that unless you are a designer who is trying to provide a model of your code to someone else for simulation, you should not normally be looking into this level of detail on how delays are modeled. Okay. Having said that, there are a couple of concepts that are important to at least keep in mind. There is the notion of inertial delay and transport delay, right? And a couple of examples will probably help to sort of illustrate that a little bit better. The idea of an inertial delay in a piece of logic is that you could, for example, have a statement like this: assign hash 5 y is equal to a. This basically effectively what it says is anytime there is a change in the value of a, wait for 5 nanoseconds and then update the value of y to that value of a. Okay. The interesting sort of corollary to this is that let us say that a changed from 0 to 1 and then back to 0 very quickly. This change will actually not get reflected in y, right. Now, why does that make sense? If you think about it, gates, as I have been mentioning at multiple times, are ultimately implemented using transistors as switches. They have certain capacitances, resistances and so on, which means that a certain amount of time is required for building up the voltages to actually transition, right, from 0 to 1 or from 1 to 0. A very short-lived pulse like this is usually called a glitch, and what glitches do is that they are almost always sort of filtered out by gates. That is, the gate does not even respond to a very short pulse at its input, right, because it takes time for it to start changing. By then the change has already got reversed and therefore the voltages just settle back to whatever they were at the start. In practice, you might find that the voltage, instead of being, let us say, 1.2 volts, goes down to maybe 1.1 or 1.0 and then comes back to 1.2, but for all practical purposes it remains as a logic 1. Okay. So, this is the concept of inertial delay, which is the most common way by which we model gate delays, right. So, a statement like this actually sort of makes sense and can be used to model a gate delay, with the important observation that if I say hash 5 over here, it does not mean I will actually get a gate with a delay of 5 nanoseconds. Okay. On the other hand, if you think about what a wire does, every single change at the input side of the wire is supposed to make its way through to the output, right. Even if it is a very small change, yes, there will be some transition, some kind of a wave propagation delay, right, but after that the output of the wire will sort of see an increase in the voltage. Then even if it is a short pulse, I would find that that short pulse basically shows up at the output as well. This is similar to the idea of a transmission line, right. Essentially what we say is, I have a change in the input, there will be a delay before the change is seen at the output, but every change in the input will effectively sort of make its way to the output and be seen there. This more or less corresponds to what happens in just wires, and therefore we call it a so-called transport delay. One way by which it is modeled in Verilog is by using a particular kind of an always block with a non-blocking assignment with a delay on the right hand side. The fact of the matter is, this now starts to get quite confusing. You have a so-called non-blocking assignment. What are these non-blocking assignments? That will become clearer when we start talking about sequential logic, right. But for now, the important point is that whenever you find that you need to model something like this, it's very rarely a good idea in practice unless you have sufficient experience with Verilog that you know exactly why you need to do this, right. So, at least at the beginning stages of Verilog, this is not really something to be concerned about at all. You should not be writing code like this, right. And as we will see later, as a general rule of thumb, when you have something like this, you are sort of trying to model combinational logic, and non-blocking assignments and combinational logic do not go well together, okay. Just to illustrate the point about the difference between inertial and transport delay, right, you can see that the input had a short pulse over here and a longer pulse over here, right. And what we can see is that in this case, this short pulse did not even make its way through to the output, but the slightly longer pulse actually showed up over here, and when it went back to 1, it basically went over here. This second short pulse again was not even seen at the output. Transport delay, however, actually showed that okay, there was a transition at time 1, after one time unit, maybe 1 nanosecond, it actually showed up on the transport delay, and every transition, you know, the falling transition also showed up after 1 nanosecond. The longer transition also showed up out here. This one also had the corresponding drop. Every one of these changes basically shows up at the output, right. So, transport delays, as I said, can be sort of seen as just a chain of transitions one after the other, right. It is possible to model this in Verilog, as I said, right. There is a test bench out here which basically tries to model the different kinds of delays, and if we run this, so you can see that in the way that, you know, it was modeled exactly like the waveform showed earlier, right. I have this A which is changing with a relatively large delay, and yes, it comes through to the output of the inertial module as well as the transport module, both with a delay of 1 nanosecond, as we can see out here, right. But the second pulse that I have over here, which is short, it is only for one time step, right, shows up at the output of the transport delay, but does not show up at the output of the inertial delay. Similarly, the sequence of short pulses that we have over here is completely filtered out by the inertial delay, whereas the transport delay sees each and every one of these changes. Finally, a larger pulse will actually make its way through both to inertial as well as transport, okay. So, this is just, as I said, a way of looking at the different models. Keep in mind that if you find that you actually need to be explicitly modeling these kind of delays in your design, it is very likely a sign that you are doing things that are probably too complicated, right, unless you know that you are exactly modeling it for use by some other system, okay. At least at beginning stages of digital design, you simply should not need to model delays at all in any form for the most part. Now, there are a couple of other keywords in Verilog. One of them is called a specify. The nice thing about it is, you know, you have this assignment statement out here, and there is a separate specify block that basically tells you about the delays between A to Y and B to Y and setup times, hold times and so on if necessary, right. The good thing is it allows you to separate out the timing specification from the actual functionality, which is actually very good news, because what it allows us to do is write code without worrying about timing at all. And later on, if we actually want to do a simulation that involves timing where we want to know the delays of individual gates, we can bring in that functionality using specify blocks in a completely modular manner without affecting our code at all, right. Once again, mostly this is used in the scenario where you are trying to do an actual delay based simulation of a circuit that you have already designed. You would very rarely need to go in there and implement the specify blocks yourself. A similar thing comes in, for example, what are called the minimum typical maximum delays. Even in FPGAs these are used, but these are more common in, for example, ASIC designs, application specific integrated circuits. And the reason for that is because when you finally synthesize and implement a circuit in hardware, it turns out that there are a lot of differences that come about due to various environmental conditions, right. The kind of process technology that was used, the kind of conditions under which a particular chip was manufactured, and also the operating conditions such as the temperature and environmental conditions or the voltage and so on, right, can make a difference to the delays through gates. So circuits are always designed under a assumption of certain minimum delay, maximum delay and so on, and it is possible to actually have simulations that use all of those different corner cases and try to find out whether your circuit will still work as expected in all of them. Once again, this is not typically done. There will be scenarios where you do the so-called post-synthesis timing simulations, but you will almost never be creating specified blocks to give these delays on your own. These are things that are created by the people designing the chips themselves, and or rather the technology of manufacturing the chips, and then they can be used in order to actually run more accurate simulations. That also relates to the idea of so-called the standard delay format, right, which is usually the final stage of modeling. After you have created a circuit, you have done everything as far as the implementation is concerned, you want to run through a simulation where you actually take into account the delays through gates and try to run it through and actually match up and make sure that everything is working properly, right. This is so-called timing simulation. It can catch certain issues that might come up due to timing errors in your design, right. And as I said, there are a number of different variations that can happen due to either process corners or environment variations or voltages and so on, which could potentially be caught by running simulations under different kinds of timing scenarios. And this SDF is a way by which different timing parameters can be specified to the simulator, and it can take those parameters and actually simulate them in all conditions, right. Once again, something which you will probably use at some point as part of doing a timing simulation, but you do not actually need to know the internal details of how SDF works unless you are getting into the realm of actually creating SDF files for others to use. So a few key takeaways. Delay modeling can actually get quite complicated. There is a good reference document on this from the HDL conference in 1999, which talks about various methods for adding delays to Verilog behavioral models. And this is worth reading because it actually makes it explicit just how confusing the delay models can be. The bottom line, if you want to summarize it, is in general, in a lot of cases, adding delays inside the Verilog code does not actually model physical hardware, right. And a rule of thumb that we can follow over here is using delays in test benches is fine. In fact, we need to do it so that we can sort of stagger out the applications of stimuli and so on. But if you use delays in synthesizable code, stuff that you are actually using to model the hardware that you want, very likely you are going to run into some kind of trouble unless you are doing it in a very controlled and very simple manner, right. Any complicated use of delays in synthesizable code is most likely going to end up not behaving the way that you expect.